everyone. My name is Hannah Turner, and I'm the president of the Marshall University Astronomy Club, MUAC. I thank you all for joining us for our Fall 2024 virtual speaker series. Drawing inspiration from our sister organization, the Society of Physics Students, SPS, which utilizes their series to spread science knowledge to the public, MUAC has created this series with the intent of capturing a glimpse into the minds of astronomers from our surrounding communities. A fundamental goal of MUAC has been and always will be to encourage astronomy discussions among upcoming generations. When we provide a platform for such knowledge to flourish, we aid a sense of possibility to all children within our local communities. Becoming an astronaut, an astrophysicist, or even a leader of a university astronomy group doesn't seem so impossible. I speak for all leading MUAC members when I say that we are very proud of what we have accomplished with this club. With that being said, I would like to introduce MUAC advisor, Dr. Sean McBride. Dr. McBride, your microphone.
Thank you, Hannah. So as Hannah has said, my name is Dr. Sean McBride. I'm an associate professor here in the mathematics and physics department at Marshall University. I really want to first thank Hannah. She's done a fantastic job helping to organize this series, reaching out to speakers, learning how to do the tech. She's just done a fantastic job. So really a round of applause for Hannah there. Thank you, Hannah. So the Astronomy Club is tied to the mathematics and physics department through me as their advisor, but it's a club that is really led by students across campus. So it's a club not just for mathematics and physics students, but everybody can be involved in the Astronomy Club here at Marshall University. Our department here is a home to a vibrant community of scholars who are passionate about exploring the intersection of mathematics and physics. In the mathematics program alone, we have over 20 faculty members. In the physics program, we have about 8 faculty members. We have programs at the undergraduate level in mathematics, physics, and statistics. At the graduate level, we have programs in mathematics, physical and applied sciences, and then pure physics. So Marshall's often been described as just the right size institution. We're not a very large R1 school, but we are an R2 school. We have about 8,300 undergraduate students and about 2,400 graduate students, and about 550 students that are in professional programs such as PharmD and MD. Close to 90% of our faculty have terminal degrees in their field. So if any of this sounds interesting to you about Marshall, please reach out to me if you're interested in mathematics, physics, astronomy, or if you're interested in something else, some other major outside of the College of Science. Still, shoot me an email. My email is pretty easy. It's McBrides, so McBrides @marshall.edu. And if I don't know the answer to your question, I will reach out and try to get you in touch with somebody that does. I'm sure if you have any questions about the information that you hear tonight with our speaker, I'm sure you can feel free to reach out to him as well and connect with our speaker. So I think with that, I will hand it back over to Hannah, and she will properly introduce our speaker.
Very well said, Dr. McBride. Thank you. So without further ado, it is my utmost pleasure to introduce our 5th speaker in this series, Dr. Thomas Troland, who will be speaking to us this evening on the Milky Way and Andromeda, a tale of 2 galaxies. This talk will span 45 minutes approximately, followed by a 15-minute Q&A period for all of our listeners to send questions within the live chat. We ask that everyone hold their questions until the end. Dr. Troland?
Well, thank you very much. It's a pleasure to give this talk to a West Virginia audience. I was thinking as I was preparing this talk that I have a certain connection to West Virginia. I grew up in New England, went to undergraduate school in New England, went to graduate school in the West Coast, and have spent almost all of my career at the University of Kentucky. But throughout almost all of my career, West Virginia has played a big role. And that big role that West Virginia has played in my career is the result of a small town that many of you have probably heard about called Green Bank. Green Bank is a really small town in a very rural area of West Virginia in Pocahontas County. But Green Bank, that name alone, is known worldwide in astronomy as the site of the National Radio Astronomy Observatory. And I have gone there over many, many years to use the facilities there. So Green Bank, West Virginia are part of my career in astronomy. And for that reason, as I say, it's a pleasure to talk to a group in West Virginia. Tonight, I'm going to talk about two things, really. Well, two galaxies, the Milky Way Galaxy and the Andromeda Galaxy, a tale of two galaxies. And you see in this image, you see part of what's called the Milky Way, which is related to the Milky Way Galaxy, but it is not exactly the same thing. I'll get into that later. And you see those dark smudges, those dark patches. Those dark patches will come into my talk coming up pretty soon. So keep those in mind. You'll see more pictures of dark patches. If you like dark patches, then this talk is going to be just right for you. So before we go further, let's just talk about where we are in the universe. Everyone knows from elementary school where he or she lives in on the Earth. You know your city, you know your state, country, and so forth. But where are we in the universe? This is also well known to a lot of people, of course, to most people in this audience, I'm sure. But of course, those of you listening now, many of you are in Huntington, and you see Huntington there on the Earth. You know that Huntington is on the Earth. There's no question about that. We all know that, just like Lexington, Kentucky, where I live. The Earth is a part of the solar system, something also that I'm sure most people learned in about third or maybe fourth grade. Our Earth being one planet orbiting the sun. And you see this illustration, which is horribly out of scale, but it gives the general sense of the situation. But what is the solar system part of? And the answer to that question is it's part of something called the Milky Way Galaxy. Now, this illustration that you see here was created by an artist to show what our Milky Way Galaxy might look like if it could be seen from a great distance out in intergalactic space. The fuzzy, nebulous colors that you see here are intended to represent the combined light of hundreds of billions of stars, of which one is the sun. That's where we live. And our solar system is just a tiny, 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 tiny part of this Milky Way Galaxy, which itself, as I say, consists of hundreds of billions of stars. And we live in what's called the disk of the galaxy. Our galaxy is quite flat. It's literally flatter than a pancake. And most of the stars in the galaxy are located in the disk. The sun and solar system are located about half to 2/3 of the way out from the center of the galaxy, from the nucleus to the edge. And here you see now that the disk itself, which is very flat, illustrated here, and the nucleus is somewhat more bulging. You see this better in this picture here. This is a picture of an actual galaxy. It's not an illustration. It's a picture of an actual galaxy. And here you see the nucleus and the disk. This is somewhat what our galaxy, our Milky Way Galaxy, would look like if we could see it edge on. Of course, we live inside the Milky Way Galaxy, so we can't see it directly as it would appear from great distance in intergalactic space. But this is more or less what our galaxy would look like if we could see it from a great distance and if we could see it edge on. It's very flat. And notice in this picture, there's some smudges that look very similar to the smudges that I showed you in the very first slide of this talk. These dark patches that you see here are very important because these dark patches, which I'll discuss more in the future of this talk, these dark patches are clouds, cold clouds of gas and dust that lie in the spaces between the stars in the galaxy. As you look at this picture, also, it's important to keep in mind that although the picture itself looks something like a fuzzy blob, as if there were a giant ball of gas in the center of the galaxy in the nucleus, really what you're looking at in this picture is the combined light of billions of stars that are actually quite far apart from each other, but you can't see them individually in this picture. There's no way that could happen. So the fuzz that you see there, the bright fuzz that you see there in this picture, including the blue fuzz you see on the outer edges of the disk of this galaxy, all that, as I say, is the combined light of billions of stars in this galaxy. Stars that, if we could see them individually, we would see that there is a lot of space between them. And in that space between them is a material called interstellar material, which consists largely of cold clouds of gas and dust. And you see them in this image here as those dark patches. Now, our own galaxy is not, of course, all that exists in the universe. I just showed you a picture a moment ago of another galaxy some distance from ours. So beyond our own Milky Way galaxy, there are other galaxies that exist in a group of galaxies, a cluster of galaxies, as it's called, but ours in particular is referred to by the poetic name, the local group of galaxies. There are about 100 galaxies in what's called the local group of galaxies, but only 2 of those galaxies are of substantial size. This is an illustration that you see here. In the lower left, you see the same artist drawing of our Milky Way galaxy, surrounded by a number of smaller satellite galaxies. And then more than 2 million light years away in the upper right is the Andromeda Galaxy, which is a galaxy that's actually slightly larger than our galaxy. It is similar in structure. It's flat. It's seen here at something of an angle, so we don't see it as a face-on galaxy, but it is a large galaxy. If you're into size in galaxies, then the Andromeda Galaxy is the biggest one in the local group of galaxies. All the other galaxies pretty much in this local group are much smaller and typically are satellite galaxies of the principal galaxies, the Milky Way and the Andromeda Galaxy. Now, how do we know about the universe? Of course, we can't go out into the universe except for some small sorties into the regions of our solar system. We can't visit most of the universe directly. So, as most people know, the way astronomers study the universe is by collecting light arriving at the Earth from the universe. And we collect light with, well, of course, telescopes. That's a small amateur telescope that you see there that can produce some interesting views, but of course, astronomers use much larger telescopes than you see here. Before we move into matters astronomical more, let me just draw some analogies right here. Sound is a wave phenomenon, and light can be seen also as a wave phenomenon. Of course, sound requires a medium to pass through, like the air of our atmosphere, whereas light does not require a medium to pass through. But anyway, with sound, as everyone knows, sound comes in a range of wavelengths, bass, mid-range, and treble. Different instruments produce sounds typically in different ranges. So I've arranged these now in terms of order from longer wavelengths or lower frequencies to shorter wavelengths. But in addition to the regions of wavelengths that encompass bass, mid-range, and treble, all of which are audible to the human ear, there are ranges of sound waves that lie outside the capability of the human ear. So there's ultrasound. Everyone has heard of ultrasound. It's used in medical imaging, and also bats create ultrasound to help them locate flying prey. There's also something called infrasound, and earthquakes create infrasound. So the point I'm making here is that there is a range of wavelengths of sound that go by the various names that you see here. And some of that range is definitely detectable by the human sensory system, and some, such as infrasound and ultrasound, is not. So now let's go to light. Now, visible light, of course, is the light by definition that we can see with our eyes. But just the way there are some ranges of sound wavelengths that we cannot pick up with our ears, likewise, there are ranges of light that we cannot see with our eyes. But here is a list now of different terms that are used to describe the various ranges of wavelengths of light. And the more technical term for all of these terms is electromagnetic radiation. Light is an example. Visible light is one range of wavelengths of electromagnetic radiation, but I'm really going to refer to all of these terms in terms of the word light. So visible light, red has the longest wavelengths, blue the shortest, and of course, a powerful source of visible light is stars. But another aspect of light is this. the longer wavelengths of light, or more technically electromagnetic radiation, the longer wavelengths are emitted by cooler material in the universe. And as we go to shorter wavelengths, as we move down the columns in this table, we are referring not only to shorter wavelengths, but we are capable of observing objects in the universe of increasing temperature. So radio waves and infrared also provide us with a way to study the coldest material in the universe, material, in some cases, only a few tens of degrees above absolute zero, material that emits no visible light. So if we can study radio waves and infrared coming from the universe, then we can learn things about cold material in the universe that we would otherwise not know just by studying visible light. Likewise, ultraviolet and even X and gamma rays, which I won't discuss in detail now. Ultraviolet, wavelengths shorter than the bluest wavelengths our eyes can detect. Ultraviolet radiation tells us about very hot material, in particular, for purposes of this present talk, ultraviolet radiation from galaxies and other objects in the universe tells us typically about the locations of hot young stars that are being formed even today in our own galaxy, in the Andromeda Galaxy, and in others. So another way of viewing this table is to realize that if astronomers could only observe a broad range of light wavelengths, from radio waves to infrared, visible light, ultraviolet, and X-rays, and even gamma rays, by being able to observe that broad range of wavelengths, astronomers can study material at many different temperature levels in the universe, and can learn much more about the universe than we could learn just by studying visible light. Visible light has been the source of almost all knowledge about astronomy up until about 100 years ago. And in the last few decades in particular, astronomers have begun using other ranges of electromagnetic radiation, other types of light, to study other regimes of material in the universe, in particular in galaxies, which I will discuss now. Here are some pictures that show various research observatories, some in space, some on the ground. Number one is a radio telescope. It looks like a giant satellite dish. This particular one, which I've used myself, is 30 meters in diameter, so that's about 100 feet. And item number three is a pair of Keck telescopes in Hawaii. And observatories 2 and 4 are observatories that are in space, because some of these ranges of electromagnetic radiation don't make it through the atmosphere, and it can only be studied by putting spacecraft above the Earth's atmosphere. Here's me at this particular observatory, which is located in southeastern Spain on a mountaintop called Pico Veleta. And some of the data, some of the images, one of the images that I'll be showing later was made with this telescope, although not by me. I've used this telescope for other purposes. Telescopes like this pick up radio static from the sky, and that material, that radiation they pick up, tells us about the cooler matter, cooler clouds of gas and dust in the universe. So here's a rhetorical question, because I don't have an audience that can immediately respond to me, but have you ever seen the Milky Way in the night sky? The question I ask my students in teaching introductory astronomy, and the answer for most students is no. If we were to go back 100 years, or even better, 200 years, before artificial illumination, everyone would have seen the Milky Way in the sky. Of course, I'm a big fan of artificial illumination. It's very helpful in everyday life, even though it's not maybe so good for astronomy. So have you ever seen the Milky Way? I didn't say Milky Way Galaxy, I said Milky Way. They're related, but they're somewhat different. If you haven't seen it, and I'll bet a lot of people in West Virginia, you have so much rural area there and regions away from bright city lights. I'll bet many of you going on camping or other trips into rural areas have seen the Milky Way. If you go out on a clear, dark night, ideally with no moonlight, and look up in the sky, allow your eyes to dark adapt, you will see a faint irregular band of light arcing across the sky. And you see that in this picture made by a fisheye lens, and the fisheye lens has a 180-degree field of view. So the dashed blue circle you see there is the horizon all the way around, and you see that arcing arcing path of light. You can sort of imagine why it was called the Milky Way. At least in some cultures, it was thought to be the result of God spreading milk across the sky. And here's another view. Here's another view of the Milky Way, also taken by a fisheye lens. This view was taken from Chile at a radio astronomy observatory in Chile. And you can see, in fact, the radio telescopes, not one, but many, along the horizon of this picture. And you see the Milky Way, or part of it at least, stretching across the sky from horizon to horizon. The center of our galaxy, the nucleus of our galaxy, happens to be in the center of this field of view. And you notice, in the previous pictures I've shown, that the dark patches that I've shown you before are also apparent very clearly in this picture. These dark patches are absorbing the light of the nucleus of our galaxy, so we don't see the nucleus too clearly in this visible light image. But in other ranges of wavelengths, we can see it much better. So two similar terms that I have just used, the term Milky Way Galaxy and the term Milky Way. These two similar terms are related, but not exactly the same thing. Milky Way Galaxy refers to this enormous group of stars, hundreds of billions of stars, symbolically illustrated in the image that I showed before, in this case in the upper right. So the Milky Way Galaxy is a huge island universe, you might say, of stars. And there are other galaxies, of course, which we see in some cases great distance, and in some cases even greater distances. The term Milky Way, however, just Milky Way itself, at the bottom of the slide, refers to the band of light that stretches all across the sky. In fact, if you could get away from the Earth and the solar system and look around without the Earth blocking half the sky, the Milky Way would be a circle of irregular light all the way around, 360 degrees in the sky. But the Milky Way, as you see in the slide here, and as stated in the text, the Milky Way is the result of the combined light of billions of stars in the disk of our galaxy. We live in the disk of our galaxy, and when we look around in different directions within the disk of our galaxy, we see a lot more light from stars than in other directions in the sky. And all that light creates that band that goes all the way around the sky, and can be seen in the picture in the lower right. Now we can ask, what causes these dark patches in the Milky Way? And the answer is that the dark patches are created by cold clouds of gas and dust that lie within our galaxy. And these cold clouds of gas and dust absorb the background light, creating silhouettes, as you see right here of the young lady. By cold, I mean really cold. These cold clouds of gas and dust, which are obviously very irregular in shape and can be seen as those dark patches, these cold clouds of gas and dust, very, very thinly distributed in the spaces between the stars. These cold clouds are only maybe 10 or 20 degrees above absolute zero in temperature. It's really, really cold out there. So now here is another view of part of the Milky Way, part of that band of irregular light stretching across the sky, which you can see with your eyes if you're somewhere away from city lights on a clear, dark night with no moonlight. And I've also put into the circle here the galactic nucleus, which, as you can see, is partially obscured by these cold clouds in front. So how do we know that these dark patches really are cold clouds? Could they not just be places where there are no stars? And the answer is we know this because we observe the Milky Way at other wavelengths of light. We observe the Milky Way, for example, in radio waves. And it turns out that when a radio telescope traverses this field of view and picks up the signals from cold clouds of gas and dust, it turns out that everywhere we see dark in this image, everywhere where we see these dark patches of light, I'll get rid of the circle, everywhere where we see dark patches of light, in this image now, this false color image of radio waves made with radio telescopes, shows that those dark regions, the dark regions seen in visible light, actually glow faintly, as seen by a radio telescope, and that glow comes from this cold material, sometimes referred to by astronomers as interstellar material. And so this pair of images, the dark patches, which are called cold clouds, The dark patches correspond almost exactly to the regions along the Milky Way of our galaxy where radio telescopes can pick up this faint radio static coming from the gas that's creating those dark clouds. So we know for sure those dark regions that we see in our own Milky Way. And we see them in the Andromeda Galaxy too. I'll talk about that later. Those dark clouds are not places where there's nothing, there's something. And the false color image you see here of the radio waves makes that very clear. I use the term false color because remember, the term color refers to that which is sensed by the human visual system. So strictly speaking, color is only applied to visible light. But of course, astronomers using radio telescopes and other types of telescopes can pick up other ranges of wavelengths of light. The eye can't see them, so there's no such thing as intrinsic color for wavelengths of light that lie outside visible light. So radio waves have no intrinsic color, for example, but when the image itself is made from a radio telescope, then the image itself can be processed and various colors can be assigned to it. And so therefore, that's what you see here. The false colors, the greens represent intermediate intensities, the blue lower intensities, the red the highest intensities of radio waves coming from the Milky Way in this diagram. So why do we care about these cold clouds of gas and dust in the Milky Way galaxy? You know, there isn't much stuff out there in some sense. The gas and dust in the spaces between the stars, the gas and dust which creates these dark patches, these cold clouds. This gas and dust is very, very thinly distributed. In fact, it's more nearly a perfect vacuum than almost any vacuum that can be created in a laboratory here on Earth. But these clouds, these cold clouds of gas and dust in the Milky Way galaxy are important to astronomers, and they've been important to my own research over many years because these clouds are the raw materials from which new stars and planets form. Our solar system formed 4.5 billion years ago. And it formed from material that was once part of one of these large cold clouds of gas and dust, which came together 4.5 billion years ago and eventually formed the sun at the center and the planets and the material that makes up us in the region surrounding that forming sun. So the study of these cold clouds that create those dark patches in the Milky Way, as seen in other galaxies, the study of these cold clouds tells us where in the galaxy stars form and how they form. And that's something that's of very great interest to astronomers. Because as I tell my own students, astronomy, like most other sciences, is not just a science of how things are now, it's just as much a science of how things got to be that way. So how did stars form? That's a major question in astronomy. For that matter, how did galaxies form? I won't discuss that now. Origins, very important topic in astronomy. Origins of stars is something that I will be dealing with in this talk. And of course, as you see here at the bottom of the slide, similar cold star-forming clouds, similar patches exist in other galaxies, not just in our own Milky Way galaxy. So now let's talk about another galaxy, in particular, the nearest galaxy to us that's similar to our own galaxy in size and shape. I mentioned it earlier. You see this diagram of the constellation Andromeda. The stars, of course, that make up the constellations are all stars in our own Milky Way galaxy. But when we look out beyond the stars in our own Milky Way galaxy, we see galaxies that are much further away. And so here you see in this diagram the Andromeda Galaxy, which it turns out is interesting because, well, for many reasons, it's interesting. But one reason why it's of interest in some sense is because the Andromeda Galaxy is the most distant object in the universe that can be seen with the naked eye. Now, it doesn't look like much with the naked eye. If you can find the constellation Andromeda in the sky and you know just where to look on a dark, dark night away from city lights, you can see a small smudge of light. And that smudge of light comes from the Andromeda Galaxy. This is the same diagram I showed earlier. It shows the local group of galaxies, our own Milky Way galaxy lower left, Andromeda in the upper right. The Andromeda Galaxy is considered by astronomers to be a very nearby galaxy. It's considered to be right in our neighborhood in terms of the universe at large. It's part of our own cluster of galaxies, the local group of galaxies. It's not far away if you don't think that 2.5 million light years is far away. Now, if you point a telescope, we have a small telescope here on campus at the University of Kentucky. If you point a telescope towards Andromeda and look at it through the eyepiece. The circle here represents the field of view of a typical eyepiece and a telescope. All you would see with your naked eye would be a faint smudge. That faint smudge would be the light coming from the nucleus of the Andromeda Galaxy. If your eyes were more sensitive than they actually are, then it would look a little bit more like this. And if your eyes are even more sensitive, it would look a little bit more like this through that same telescope field of view. And if your eyes are even more sensitive, it would look like this. And if you could see a greater field of view, it would look like this. This is now a picture, obviously made with the time exposure, of the Andromeda Galaxy. The Andromeda Galaxy, as I say, is very similar to our galaxy in structure. Although we see it somewhat nearly edge on, not quite. You see the nucleus in the center. You see two companion galaxies, smaller galaxies, one below and one above the Andromeda Galaxy. When you look at this picture, the stars that are randomly distributed all over the field of view, those are all stars that are nearby, relatively speaking. All those little points of light scattered around this image are stars in our own galaxy, much, much closer to us. And we look out through that veil of nearby stars in our Milky Way Galaxy to see the Andromeda Galaxy much further away. And also, as I mentioned in a previous moment in this talk, when you look at an image like this of a galaxy, it almost looks like a giant fuzzy cloud of gas. But really what you're seeing here in this image, like in other images of galaxies, really what you're seeing is the combined light of billions of stars. And even in the nucleus that looks like that bright blob, even in the nucleus, those stars are far apart from each other. If we could see them individually, we would see that there's a lot of space between the stars. But there's so many of them, hundreds of billions of them, that in any picture like this, that light simply spreads apart, or comes together, I should say, and appears just as one continuous blob. Now, as I said, the Andromeda Galaxy is similar to ours. It's a flat galaxy with a somewhat bulging nucleus. If we could see it face on, rather than edge on, sort of here in this diagram, if we could see it face on, it might look something like, not that, that's the moon for size comparison, like that. I have simply digitally stretched the image that I showed you earlier. And here you see now roughly what the Andromeda Galaxy would look like if you could see it face on. But we don't see it that way. We see it like this. And the moon, as I said, is shown in this picture to give you a sense of the scale in the sky. The Andromeda Galaxy, if you could see it, if your eyes were sensitive enough to see it as you looked up at night, and not just see the nucleus, but the whole galaxy, it would be more than twice as big in the sky as the moon. So let's go back to waves of light. I'm going to show you a few pictures here of the Andromeda Galaxy made in different wavelength ranges of light. I'll show you a picture of the Andromeda Galaxy in visible light. I'll show you an image of the Andromeda Galaxy with radio waves, which tells us about where the cold gas is in this galaxy. I'll show you a picture of the Andromeda Galaxy in infrared light, which will show us also about these cold clouds of gas and dust. I'll show you a picture of the Andromeda Galaxy in the ultraviolet light as well, which brings out the emission from hot young stars. And so we can study these different ranges of light. Radio waves and visible light can be studied from the ground because both visible light and radio waves typically make it through the Earth's atmosphere easily. Infrared, ultraviolet, and for that matter, X-rays and gamma rays do not in general make it through the Earth's atmosphere. So they only can be studied by space-borne observatories. So here we are. Here's another picture. Here's another picture of the Andromeda Galaxy. And if you look at this picture, you see those dark patches. You see those dark patches in the Andromeda Galaxy that are the same sort of thing as the dark patches I showed you before in the Milky Way. So the Andromeda Galaxy has these cold clouds of gas and dust. And those cold clouds of gas and dust are shown here as those dark patches, just as they are in our own galaxy. Now let me show you what this galaxy looks like if it is observed not by an ordinary telescope, visible, sensitive to visible light, which is what you see here, but if it is observed by a radio telescope, in fact, that radio telescope up on the mountain in Spain that I mentioned some time ago. But before I do that, this is a hand-drawn shape. I just did this by hand in PowerPoint. This is a hand-drawn shape which traces out some of these cold clouds. So let me take it away. and then put it back, and then take it away and put it back. And as you can see, this hand-drawn irregular shape does in fact indicate the location of some of these dark patches in this galaxy. Now, let's take it away. Here is now an image made with a radio telescope. It's a false color image, like all images of radio telescopes. And if you look at this image, you can see that the regions in this galaxy where the radio waves are coming from, that is to say, the regions in this galaxy that have these cold clouds are indeed the regions where we see the dark smudges, the dark patches in visible light. So what is dark in this picture of the Andromeda Galaxy? The tendrils, the filaments of darkness, which are in fact silhouettes of clouds of cold gas in this galaxy absorbing background light. They correspond in position almost exactly with the radio waves. And here now is that very same shape, which I've drawn earlier and superimposed as well. So what we can see is that towards the Andromeda Galaxy, like our own galaxy, the radio waves that are picked up from cold clouds trace nearly exactly the dark patches that we see. Another indication of those dark patches in Andromeda, just like the dark patches in our own galaxy, are not regions where there is a void of stars, but rather are regions where there is cold material too cold to emit light, but it does emit radio waves and can be seen and detected and mapped by radio telescopes, like several that I've shown you. And for example, like the telescope at Green Bank, the Green Bank telescope, which is also capable of making maps like this. Now here's another image. This was made from space. This was made from a orbiting observatory called Herschel, which was in operation some years ago. This is also a false color image because it was made with infrared sensitive detectors. The eye can't see infrared light, so it has no intrinsic color, but the color chosen here was the color red, because people associate infrared with red. So here you see now a beautiful image of the Andromeda Galaxy. What you're seeing here is light from these cold clouds, but in particular the dust, small pieces of dust that lie among the gas in these cold clouds, in this case, the Andromeda Galaxy. This is a beautifully detailed image. You don't see the stars here because stars don't emit this type of infrared light. So when you look at a picture of the Andromeda Galaxy, it's detected by an orbiting observatory, which is sensitive to this infrared light. All you see are these clouds of gas and dust. You don't see the stars because the stars don't emit this radiation. But here's that little diagram. Here's that little shape that I showed you before. And you see the regions where this dust emission is brightest are also the regions where the visible light picture shows the dark patches and where the radio waves come from as well, because this same shape, the same shape shown in blue here, this same shape is exactly the same in these slides that I've been showing you. Here is now a picture of an image of the ultraviolet light. It comes from hot young stars. The cooler stars, which are far more numerous in the Andromeda Galaxy. The cooler stars don't emit much ultraviolet light. It's the hot stars, which in general are young stars, recently formed stars, maybe only in the last 10 million years ago. That's a very short time in astronomy. So here you see now the Andromeda Galaxy in the light of ultraviolet, which is almost exclusively coming from young hot stars. Here's that same shape. And the same places where we saw the dark patches in the visible light, the same places where we saw the infrared, and the same places where we saw the radio waves are the places where the galaxy is also bright in ultraviolet light. And what does that tell us? What does that tell us? Well, the answer is, here are the radio waves once again. What that tells us is that those dark patches that we see in Andromeda coincide with the radio waves from the cold clouds, with the infrared light from the cold clouds, and with the ultraviolet light from the hot young stars. So what that tells us, and this is an important conclusion, what that tells us is that these dark patches in the Andromeda Galaxy, and the same could be said about our own galaxy, these dark patches in the Andromeda Galaxy are the regions where there are these cold clouds that emit radio waves and emit infrared light. And these are the regions also that are lit up in ultraviolet light from young hot stars. So these are the regions where the stars are forming in the Andromeda Galaxy. Like our galaxy, stars form in the Andromeda Galaxy only in certain places. They don't form everywhere in the galaxy. And they're forming today. They're forming today in these dark patches, these clouds of cold interstellar material that is brought together by its own gravity, causing the material to heat up and eventually form new hot stars. So if you ask, where do stars form in a galaxy? Where do stars form in the Andromeda Galaxy? The answer is in these cold, dark clouds, they form. But of course, the process of forming stars, which itself takes hundreds of thousands or several millions of years, that process itself involves converting the initially very cold material in the cold clouds into much hotter material, which we call stars. Now, if you don't think you can get a good enough view of the Andromeda Galaxy, I've got good news for you. Andromeda is coming, not the redcoats, but Andromeda is coming. Andromeda is coming. Here we are now, 2.5 million light years away from Andromeda, but it has been determined in the last decade or two that Andromeda is approaching us, or we're approaching Andromeda, same thing. There is a very decent likelihood that the Andromeda Galaxy and our galaxy will collide in the future. Don't worry, it won't be anytime soon. It'll be in maybe 3, 4, 5 billion years or so. These things take time. So now the two, apart from each other, 2.5 million years. Here is now an illustration, and I'll show you several in this series. Here is an illustration that shows the Andromeda Galaxy today. You see the arrow pointing to it, kind of off in the distance, and you see part of the Milky Way, that is light from the stars in our own Milky Way galaxy. So this is where we are now, with the Andromeda Galaxy appearing somewhat off in the distance, but let's move forward 2 billion years. The Andromeda Galaxy will be getting closer. It'll be a nicer view, I guess. And then by almost 4 billion years from now, it'll be even closer. That's going to be something. You know, I wish I could be put into a freeze locker and brought back to life maybe in 3.75 billion years and look up in the sky and see the Andromeda Galaxy. But it's going to get better than that, because by about 3.9 billion years, the two galaxies are going to collide. Actually, they're going to pass through each other. Because when galaxies collide, the stars in one galaxy are extremely unlikely to collide with any stars in the other galaxy, because stars are very far apart compared to their sizes. So two galaxies can actually collide without the expectation that a single star in one galaxy will collide with a single star in the other galaxy. But what happens is when they collide, the gas in the galaxies, the same gas that is making new stars in our own galaxy today, when two galaxies collide, the gas between the stars gets compressed, and that stimulates star formation. What you see here, all these colors and so forth, are the result of star formation that will be taking place on an enormous scale when these galaxies collide. It's going to be a mess. It's going to be a mess. But the chances of our solar system colliding with another star from the Andromeda Galaxy are almost none at all. After the two collide, so to speak, the thinking is that they will move past each other. They'll temporarily move apart, and this might be what the sky would look like from the Earth. You see the Milky Way there rising up from the mountains at the bottom, severely distorted. The Andromeda Galaxy is severely distorted because as these galaxies approach each other, the gravity of each galaxy severely distorts the shape of the other galaxy. So the galaxies lose their nice, tidy appearances they had before the collision. 5 billion years from now, the prediction is that there will be a second approach of these two galaxies. They come back together and they begin to merge. 7 billion years from now, by some predictions at least, our galaxy and the Andromeda Galaxy will have merged into a single galaxy with a very different shape. It'll be much more rounded, a type of galaxy that we see in the universe today, a type of galaxy called an elliptical galaxy. In this case, a giant elliptical galaxy. Now, this is an illustration like the last slides I've shown. 7 billion years from now, if all goes well, so to speak, our galaxy and the Andromeda Galaxy may have passed through each other and come back together and eventually merged into this giant elliptical galaxy. Here is now a real picture. Here is a real picture, not an illustration, of such a giant elliptical galaxy. This particular galaxy, as you see, is about 50 million light years distant. So it's much more distant than the Andromeda Galaxy is today. And astronomers think that large galaxies like this galaxy probably contains 1 trillion stars. 1 trillion stars, that's 1,000 billion stars. In the picture, you can't tell that. All you see is that hazy light. But the hazy light you see of that giant galaxy in the middle of this picture, that hazy light is the combined light of maybe 1 trillion stars, stars that are actually quite far apart from each other, but their light merges together into one fuzzy blob. We think this galaxy here has been built over the history of the universe by a number of successive collisions and mergers with other galaxies. So it just gets more and more mass, more and more material, more and more stars over time. And this is a process that we know is happening because we see this in the universe. We can't look at the collisions of a galaxy like this because they occurred in the distant past. Here is now another real picture. Here are two galaxies colliding with each other. Now, the collision might take hundreds of millions or even a few billion years, so we can't see the whole collision take place. These galaxies are coming close to each other. The gravity of each is severely distorting the other, and they may well merge at some time, maybe 500 million years from now, maybe 1 billion years from now. We don't know. Here's another example. These two galaxies are very close to the process of merging into one, each one distorting the other. And the blue light that you see there comes from recently formed stars, because when galaxies merge like this, when they collide, the collision of the clouds of gas in each galaxy with those in the other galaxy stimulates star formation. And the blue you see there is an indication of recently formed stars. Here's another example. Here's another example of that. These two galaxies are very close to full collision, full merger. And the brown that you see there, this is a real picture. This is not an illustration. The brown that you see there is material from cold clouds of dust that have been squeezed together and will, in the relatively recent future, recent astronomically speaking, they will form new stars. A whole symphony of new stars forming as these two stars collide, two galaxies collide. And these two galaxies, maybe 2 or 3 billion years in the future, will very likely become one settled down, roundish, less dramatic galaxy, namely a giant elliptical galaxy. So Andromeda is coming to get us, or we're coming to get Andromeda. But the good news is it won't happen anytime real soon. So for those with lots of patience and billions of years to wait, there's something to be seen in the sky. But for the rest of us, we'll just have to wait. But astronomers can look up into the sky today with their telescopes. These are all Hubble Space Telescope images. And they can see in many directions in the sky, distant galaxies in the process of colliding with each other. And in most cases, those collisions we think will create mergers of the stars from the two galaxies into another, even larger galaxies. So if you like collisions, then the universe is full of collisions of galaxies. So that's all, folks. That's all I've got. And I would welcome any questions that anyone might have.
Dr. Troland, that was wonderful. Thank you. I will say I particularly enjoyed your false color image of the Andromeda Galaxy. It was beautiful.
Well, I'm glad you enjoyed it. That's one of the things I like about astronomy, which fundamentally is a quantitative field, of course, but there are lots of really interesting images that come from astronomy. And so in teaching introductory astronomy, I love the fact I can show those images. This is not an interesting image. That growth on the top of my head has since been removed, you'll be glad to know. Let's just look instead at this picture here while we await any questions that may come in.
Dr. Troland, while we are waiting for anyone who may have questions, I'm sure myself as well as Dr. McBride may have a few for you, if that's okay.
Sorry, I did not hear that.
So while we're waiting for questions from our concurrent viewers, I'm sure Dr. McBride as well as myself has questions. So maybe we could go ahead and direct those towards you and you could answer them.
Stop sharing, you said? Sorry, no.
I have questions as well as Dr. McBride. So maybe we can go ahead and ask you those if that's okay.
Sure. If others, apart from the two of you, have questions, I'd be happy to address those, but let's start with any ones you may have.
Wonderful. So first off, I had truthfully came into this talk with the intention to ask you about the anticipated collision between the Milky Way Galaxy as well as Andromeda, because I've done some reading on that, so it's very interesting. Now, I have read that the collision of the Andromeda Galaxy with the Milky Way would result in a larger galaxy that would, correct me if I'm wrong, be more so elliptical rather than spiral. Is that
Yes,
correct?
correct, correct.
So, with an elliptical galaxy, again, please correct me if I'm wrong, I've read that there's more so random star motion than orderly rotational motion. And so, would this not hint to stars not orbiting necessarily its galaxy center? And if so, to what extent would differential galactic rotation, or the phenomenon in which objects farther from the center take longer to complete an orbit around a galaxy rather than those closer to the center, still be applicable?
Well, I think the time in a giant elliptical galaxy or an elliptical galaxy, the time for a given star to make sort of an orbit would not be much different from the time that our solar system today takes to make an orbit around the center of our galaxy. As you were saying, motions of stars in a organized galaxy and a spiral galaxy like the one we live in and like the Andromeda Galaxy, those motions are principally circular motions around the center. Our solar system and the stars near us in our galaxy take about 250 million years to make one complete circuit around. But when two galaxies merge, imagine two flattened disk-like galaxies, such as the Andromeda Galaxy and our own Milky Way Galaxy, when they merge, then that symmetry is lost. And so, as you said, the stars, each star has its own orbit, but it's not really an orbit in the sense of orbits around the sun in the solar system, because the motions of stars in an elliptical galaxy are somewhat irregular. They don't have closed orbits. They don't ever come back to where they started from. So they simply move in various ways. And no two, quote, orbits of a star in an elliptical galaxy would be the same. It'd be very different. I'm not sure if I've answered your question, but if not, feel free to tell me.
You did, thank you.
Okay.
Dr. McBride, do you have any questions?
So one question I have is, I always like to think about our audience that maybe we're connecting with some younger viewers out there. And let's hypothetically say that, through the images and information that you provided, you have sparked the interest in a young student out there that is literally dragging their parents outside right now to try to look and see some of these things in the sky right now.
Yes.
What advice would you give that student or young individual right now that is now super excited to get into astronomy? What would your advice be then? Say they're in middle school. How would they prepare themselves for a track to get to where you're at right now? What would you give that advice to somebody that's in middle school that is now just super excited?
Well, I would say to someone in middle school who perhaps would be interested in astronomy, and that was in fact me many, many, many years ago, I would say, learn as much about astronomy as you can. There's lots of things to read. There are, of course, a lot of web resources, and your science teachers perhaps can direct you to various resources. Learn about astronomy as much as you can. And also, I would say, learn as much about mathematics as you can, because astronomy, well, you know this, of course, but astronomy is a quantitative field. So people involved in research astronomy do make frequent use of mathematics. And so someone who is interested in astronomy but has little interest in mathematics, I would say, is probably not a good candidate for someone to go into astronomy professionally. So if you're a middle school student, hone your mathematics, take science courses, take a physics course if it's offered, or a physical science course. When you get to high school, make sure you take math courses and also take physics courses. If there's an AP physics course and you're up to that, why take that? Try to, in short, in your middle school, but especially in your high school career, try to learn as much about mathematics and physics as you can, while at the same time finding out about astronomy as interests you. Then when you get to the university level, the best bet for someone aspiring to a career in astronomy, the best bet for someone aspiring to such a career would be to major in physics. You could do that at Marshall, you could do that at WVU, you could do that at just about any school, especially our state university, which generally tends to have more in the way of offerings in these fields than smaller liberal arts schools. So as you go through your educational career up through undergraduate years, middle school, high school, undergraduate years, become involved as much as you can in physics and in mathematics. And then, of course, if you're going into research astronomy at a professional level after the undergraduate phase, and of course you know this, you would then go to grad school and ideally work for a doctoral degree at a graduate program, and then go on with your career. So that's sort of the path to astronomy in terms of a career is through physics and mathematics, especially earlier in your educational career, as much as possible.
Thank you.
My father was a high school science teacher. He taught mostly chemistry in the high school I attended, but he also taught an astronomy class. He got me interested in astronomy because he had an interest in that. It was not his field. His field was chemistry, but he got interested in that. And so he got me interested in astronomy. He offered a one-semester astronomy course when I was a senior. I took the course, and I got an A in that course. And if anyone doubts me, I'm sure you don't, of course. Why would you? But no, who cares? But my father passed away many years ago, as you can imagine, someone my age. And I was cleaning out the house, and I found a big stack of his grade books from high school, going back many years. I discarded all but the year from my senior year when I was in high school. I kept that grade book of his, and in that grade book is my name and my grade. So, and then there was another student in the class whose name was Kenny, and I noticed that his grade was F plus. I could not figure out exactly what the point of an F plus is, but anyway, I don't think he was much interested in astronomy. This other student probably did very well in life, for all I know, hopefully. Anyway, that's the story regarding a career in astronomy. When I do hear students say, I'm interested in astronomy, but I don't like math and physics, there's nothing wrong with having that perspective. But then what I would tell them is, if that continues to be the case, fair enough. But for you, astronomy might be something that would be an avocation, something you'd be interested in pursuing just for your own interest rather than as a professional career. And that's an interesting thing to do. One of the things I love about astronomy is that, as you well know, it's a field of science which is of interest to a lot of people, even people who are not into science at all. There are amateur astronomy clubs. You have a club at Marshall, for example. We have a club here, not affiliated with the university, but a club of amateur astronomers, Bluegrass Amateur Astronomy Club. People love this stuff. Some do. And I love teaching it because you're teaching about things which many people have something of an interest in.
Well,
Anna has an interest in it, obviously. So
that fits the bill for one of our astronomy club members. He has a passion for astrophotography, and he's really good at it.
yes,
But maybe some of the hardcore science classes he might not necessarily have a passion for. But the astronomy side of things and the astrophotography, he does an amazing job at that, and he's very passionate about that. So there is definitely students interested in astronomy at all different levels.
yes, that's a good way to put it. It is amazing what amateur astronomers with a lot of patience and a little bit of money, but it doesn't take a huge amount. It's amazing what kinds of images they can create. It's just with electronic detectors and image processing capabilities and digital imaging. Some of the images I have seen coming from amateurs, including some right here in Lexington, are as good as any observatory could have created maybe 20 years ago. I mean, it's just astonishing.
Mm-hmm.
Just astonishing. So that's an interesting hobby. It requires patience, though, and willingness, of course, to stay up late at night, and also requires willingness to hang out and say cold weather sometimes. So it's not for everyone, but astrophotography is definitely something that's a fascinating hobby for those who find the universe fascinating, but may not be necessarily interested in a professional career in astronomy.
Dr. Troland, I'd just again like to thank you for coming and giving this talk for a virtual speaker series. We've truly benefited from your presence and everything that you've had to say, so thank you. We did have 2 comments come into the live chat. So first off, from Dr. Laura Stapleton, she said,
Yes.
Dr. Roland. I don't have any questions, but I just wanted to say how much I enjoyed your talk. I
Oh,
learned
very-
so much. Also, I'm a mathematics teacher, and I thank you for the shout out to mathematics.
Well, very nice. Very nice. Well, thank you. I enjoy giving talks about astronomy. I've done so for many, many years. I've told people I've talked to groups of all ages, from pre-kindergarten to senior citizens, of which now I'm a member. So I enjoy doing this as a sort of public outreach. And I think it's great that you have a program like this at Marshall that sponsors talks like this and makes them available to students. So I appreciated the opportunity to be able to give this talk. Thank you.
Yes, again, thanks for donating your time tonight. We really do appreciate it. And it was a fantastic talk.
Will this talk be, will a link to it be on your website? I'd be interested in just seeing how you set this up. We have a similar series of talks here at the University of Kentucky. We call them Kentucky Sky Talks, and we've been putting them on YouTube too, but I don't think it's worked out as well as I would have liked. I bet you do it better. So if you would, Hannah, if you would send me the link, or maybe if you'd send me the link for this talk or other talks, in fact, you may have, or just a web page that has those links, at some point, I'd appreciate that. So,
Of course, I can do that after this talk ends tonight. So,
sure, there's no hurry, anytime, at your convenience. So, okay, very good. I guess we're done then, as far as I can tell, or is there anything else? Is there anything else to do?
no, that's it.
Okay.
Thank you for your time.
Thanks
Okay,
again.
very good. Okay, very good. I hope that somebody listening to this talk, either live or maybe later, will be motivated to go out some dark night and look up and find the Milky Way. A lot of people have never seen it, but I imagine there are plenty of places in West Virginia, as there are in Kentucky, where you can see it. They just have to be away from city lights. So there you go. I tell my students, that's your homework assignment. Go out some night when you're out and camping or doing something away from city lights, and it's nighttime and clear and dark. Your homework assignment is find the Milky Way. I tell them it won't be hard to see if your eyes are dark adapted, because you'll just see it arcing across the sky. So anyway, there you have it. So long. So good to talk with you both, and I enjoyed giving this talk.
Thank you.
Thank you.
Okay.